Hello everyone, welcome to the third lecture of the Gravitation chapter of class 11. I am Abhimanyu Singh. I am first year undergrad at IIT. So we are going to start this third lecture now. So first we will be recapping the what we have studied earlier. So in the last lecture we studied about field and potential of various objects. Like we studied about a ring. The potential due to is like minus gm by r square plus x square. The field is gm x. So this was the field. Then we studied about spherical shell uniform inside inside the potential is constant given by minus gm by capital R, which is the radius of the spherical shell. Outside it is given by gm by small r. And then we studied the field inside the spherical shell. The electric field is zero, and outside it is just behaves as the point charge kept at its center. As the point mass placed at it, it is a constant quantity, so its differentiation gets zero. And then we studied about spherical solids. It is filled, so the potential is like quite tough. Let me write it: minus gm to r cube, and for outside it is just a point mass placed at the center, and the field is like r cube, and outside it is. So this was like this. And then we studied about the variation in value of g, and we came to know about that value of acceleration due to gravity. This is what field and potential we discussed. And then we discussed that value of g is nothing but the value of electric field at that point. Sorry, the field at that point. The value of acceleration due to gravity is nothing, just the value of field at that point. And we discussed like on the surface, it is like gm by r square. We discussed about on moving height h, what happens. So we see that on moving height h, when h is small, it is like the direction comes out to be 1 my g new g divided by g is initial g is equal to 1 minus 2h by radius of earth when h is small. And when we move inside h depth, we came out, the new relation is like g prime by g is 1 minus h by r. So this is it. And so now we are going to start the new class. Firstly, in this class, we will study effect of rotation, which we also discussed slightly in the last class. We will start the class by this, and then we will move to like satellite, which are one of the most important aspects to be covered in this chapter. We will studying about satellite, geosynchronous, geostationary, and then we will move towards like orbit analysis, how orbits we can find the orbit. We we will be discussing what is the shape of orbit in the later classes. Like in the next class, most probably we will discussing how to decide what is the shape of orbit, like whether it will be circular one, it will be elliptical, it will be like parabola, hyperbola, or what. We will discuss in the next class, but we will in this lecture we will see if we know that the orbit is elliptical, how to analyze this orbit using the energy analysis, which is quite common one. So first of all, variation of g due to rotation of Earth. So Earth is like itself accelerated thing. Like Earth is already accelerating, and we know that Newton law of gravitation, Newton laws are not valid in accelerated frame of reference. So for to get rid of that, we like use the concept of centrifugal force. So this is like the centrifugal force, and that the object is rotating in the circle. So there should be a centripetal force, and when we solve this, and when we find the value of the new normal, like using the parallelogram, you can say when we write it, we get it like this. mg square mr square omega square 2 mg square omega square cos 180 minus theta. And when we solve it, we get it g is equal to g minus omega square r cos square theta. You can easily remember it by the dimension g dash minus g omega square r is the dimension of acceleration into cos square theta. You can just say that it is just the centripetal acceleration uh, of an object moving in a circle of radius r cos theta, where r is the radius of the earth and theta is the latitude angle of the latitude. Like if it is like theta, so this is like this. So, but due to continuous rotation, the shape of Earth has also changed. Like on one side, Earth is smaller, and one side it is its radius is less. So we need to consider that. So even without considering the effect of rotation, we have like r prime. Just suppose, let me draw it. Where is my cursor? R prime. That is the radius at the equator. So r prime is greater than r. That directly implies g is greater than g prime. So the inequality gets reversed because g is gm by r square. So g is at pole. This is pole. This is obvious. This is equator. So the value of g is maximum at poles. So like, so this is like this. Okay. And so now this is like the all we have covered about the variation and g. You can see this like diagram again. Okay. So this is mg. Like this is a particle here. This is mg. Okay. And this here is like the centrifugal force. This is the pseudo force. And when we find the value of g effective, comes out to be this direction. Okay. It is like g prime. So now we will move on to like orbit analysis. Like suppose the satellite is moving around the Earth in a circular orbit, where RE is the radius of Earth and RS is the radius of the circular orbit in which the Earth is rotating. So, so as we know that the acceleration is nothing but omega square r, or the centripetal acceleration, which is needed for the satellite to move in the circular orbit. In the radial direction, this is the only direction. However, it may have some acceleration in tangential direction, but we are considered only in radial direction. So the acceleration is nothing rs omega square r cap. And when we apply the like the Newton law, what is Newton law? Newton law is sigma f external is equal to ma, all in vector. This is the Newton law, and the only external force here is the force of gravitation. So we know that the force of gravitation is this. So when we equate the component, we find it to be like this, and we will find it r to be this and this, and then we move further, and when we put omega is equal to 2 pi by t, okay, omega is 2 pi by t, so we get t square. In this equation, we are putting this and squaring it, like cubing it. So we get t square is equal to 4 pi square a cube by gm, where m is mass of Earth. So this is what we have find t square proportional to a cube. This is the Kepler law of orbits. Sorry, Kepler law of period of time or whatever it is. It is Kepler's third law, which stated that t square proportional to a cube. So we got it. But here, like it is in circular orbit, but Kepler predicted it for like the elliptical orbit. But we can have a elliptical circular approximation. Like suppose an Suppose we have like elliptical, an object rotated in elliptical orbit. So it will be have R max, which will be equal to A plus AE. Suppose it is rotating, the sun is here, Earth is like here, and so the maximum distance will be A plus AE, and the minimum distance will be A minus AE. So, and when we find the average distance, we approximate it to be like a circle of radius A. Because for approximation, we use like R is equal to R max, R mean divided by 2. This is the formula we use for circular approximation, and thus the radius comes out to be A only. So, and, and so the moment in ellipse, it can be like approximated into a circle of the radius equal to its semi-major axis. However, it is incorrect, but we can approximate it to see that our result is a similar one. So now we will be discussing about geosynchronous and geostationary satellites. So geosynchronous satellites are those which first of all we will discuss like geostationary satellites. Geostationary satellites are the satellites which revolve in the equatorial plane, as you can see in the photo, and it is like above around 35,786 kilometers, and which seems to be appear at rest with respect to Earth. Always, they are always with respect to Earth. Whenever we see from Earth, and it always lies in the equatorial plane. And the geostationary satellites are like the satellites having time period is equal to the Earth time period of rotation, which is 24 hours. But instead they have like they are not in the equatorial plane. They are like at an inclined plane or something like that. So it has numerous applications such as television, broadcasting, telecommunication, etc., etc. So now we will be moving towards like the analysis of elliptical orbit. So we know about that gravitation is central force. And in central force, we have conservation of two quantities, like the total energy is conserved and the angular momentum is conserved. Why the angular momentum is conserved? We have studied tau external is nothing but dl by dt. We know that. So, and it is also is equal to r cross f. We know that in central forces along the radius direction. So, r the angle between the force vector and radius vector is 0 degree. So, their cross product turns out to be 0. So, that implies dl by dt is 0. So, dl by dt implies that the change in angular momentum is 0. So, the angular momentum must remain conserved. So we have two, and the total energy remains conserved. As there is no non-conservative force like friction, obviously there is friction, but we approximate like there is no friction, no air resistance. So there is energy conservation. So while studying elliptical orbit, we use these 2 points: conservation, energy conservation. So suppose first we will see like how we conserve the angular momentum. This is R1, this is V1, this is R2, this is like V2, and suppose this is some general arc, and here the velocity is like this, and the angle between the radial vector and velocity vector is theta. So from applying angular momentum conservation, we have like m r1 v1, as at these 2 points the velocity is perpendicular, so there will be no sine theta term. We know that the formula is like r cross p, so it is just like r cross v because mass is a scalar quantity. We take it outside. R1 V1 is equal to M R2 V2 is equal to M RV sin theta. So M get cancelled on all the three equations and we get this equation. R1 V1 is equal to R2 V2 is equal to R1 V1 RV sin theta. So this is the first equation. And now we write the orbit terms. So first, the potential energy. Suppose we are writing at this R1 position and then with R position. So it will be like G N N R1 is equal to half M V1 square by R plus half M V square. So here we have like we have R1, V1, R and V2. We have four quantities. Generally, we know three of them, and we know two of them. We need to find the other two. So we will be knowing like R2, V2, and we need to find either R or V, and we also know the theta. So we will just like we just substitute uh, R in the form of V or V in the form of R, and then we calculate the further calculation according to our need. So this is the mostly like the most important two results. We first apply the angular momentum conservation, then we do the energy conservation. So this is the basics of the elliptical orbit. Now we will be moving towards something how to decide which orbit is which. But before that, let us say let us discuss the concept of escape velocity, the velocity required to send the object beyond the gravitational field of Earth. So this is like the escape velocity. So how do we calculate this? So let us calculate how. Suppose this is a radius m mass r e, whatever it is. So here is the object. Here is the object. We want to send it to like very far. And suppose it reaches there with zero velocity in the optimum case. If we give it, it is the bare minimum energy at which it reaches there at zero velocity. So fine. Initially we have half mv square, which is the escape velocity. Okay, and the potential energy, mass of Earth, mass of object divided by radius of Earth. So it is like is equal to zero because when it reaches at that point, so Earth gravitational field is no valid on, and we assume that there is no other field. So its potential energy turns out to be zero, and we are considering the optimum case, the bare minimum velocity, which is needed. So it reaches there by a zero velocity. We assume that, and if we give it more energy than this, what is the energy? What is velocity we are giving? Then it reaches there with some kinetic energy as well. So it depends upon the energy conservation. Like, and when we do it, we get V is root 2 gm by r. What was the velocity required for an object to move in a circular orbit? So it was like root gm by r. So it is just root 2 times. Suppose we say root 2 we know. Suppose questions come like by how many times the velocity must be increased in order to send a satellite revolving around the surface of Earth to like infinity. So we will say that we need to increase the velocity by root 2 minus 1 v naught times in order to send it beyond Earth field. So this is like this. And now as we have discussed the escape velocity concept, we will be discussing the concept how to decide the orbit of the object, like which type of object will be revolving in which type of orbit. So as we are going to see which type of orbit and how to decide it. So energy is majorly the parameter to decide which type of orbit will be there. Energy is the most important parameter to decide. So we use energy, mostly kinetic energy, and what is the initial velocity given to it. So like till now we have studied like two kind of velocity. First, it was the velocity required to in a circular orbit around any in gravitational field. And secondly, we have studied about escape velocity, which is required to move in to send it outside like this. So, so let's just say first, if we give a velocity is equal to v naught, that is root gm by a, it will be a circular orbit. Not perfectly, but we assume it to be circular at that exact value, circular. If we give a like a velocity ranging between v naught and root 2 v naught, which was the escape velocity, we will have a elliptical orbit. We will have a elliptical orbit. Now, suppose if we give a velocity is equal to exactly is equal to the escape velocity. Now we will have a parabolic orbit, bolic orbit. And if the velocity is like greater than root 2 v naught, we will following a hyperbolic orbit. As as many of you are not aware with conic sections, so let me show you some of the shapes. How does hyperbola look like? Hyperbola looks like this. I think it's clear. This is hyperbola. And so the planets just move away towards the infinity. It is just like this. And how does parabola look like? It looks like this. So like here it also moves towards infinity. It is not a closed curve, it is unbounded. It moves towards infinity. So it is like moving. And in ellipse, you know ellipse. I have brought ellipse. But let us see again. So this is the ellipse. Let me draw a diagram to show you clearly. This is the circular path. When the circle and if the velocity is like that, then it will not move in circular orbit. It will just fall down there. If the velocity is like, then this orbit. If the velocity is more than this, it is the elliptical orbit. If is like less than, and if it is parabolic, it will be like this. It will move like this. First, we have a circular orbit, and then we have a elliptical orbit, and then we have a parabolic orbit like this. It will move towards infinity. Then we have hyperbolic orbit. It is the hyperbolic orbit. This is like this. If the velocity is less than v naught, then it will not form any kind of orbit. If the velocity is equal to v naught, which is root gm by a, it will form a circular orbit. If it lies between the range of circular orbit and the escape velocity or velocity, then it will move in a elliptical path. If it is equal to the escape velocity, it will move towards infinity in a parabolic path. It will not move in any kind. It will not be in orbit. So orbit can only exist in the range v naught to root 2 v naught and not in other range. So like, and this point is called perigee and the other point is called aperigee. So I think we have covered mostly the concept in this chapter. So I think the theory part is almost finished in this chapter. We need to do some more problems. We will be seeing more problems in the other classes, but as of now, the theory portion is completed. I think this is it. Like that, we are finished with the theory. In the next class, I will be discussing some of like extra concepts, mostly not for like just for JEE purposes, not for like your school exams, and then we will do some of the problems in the next two lectures. Okay, thank you very much. Have a nice day.